There we go. This is, so that was the instrument, and now supporting the instrument is the spacecraft bus. These series of images shows how you take a large block of aluminum and quickly, in a few steps, convert it into a monolithic spacecraft bus. It actually takes many steps. You can see that they went through rough machining, fine machining, and they're testing they're assembling the panels there, and then you end up with a full spacecraft bus with all of its components inside. The spacecraft bus includes a pointing system, a power system, and all the components of a large spacecraft bus. The next image is the observatory fully assembled. This is coming out of thermal vacuum testing. You can see the spacecraft is now at the bottom of your screen and the instrument is at the top of your screen. The next movie we show, it will be of the observatory coming out of vacuum testing. There you go. And this is it being prepared after vacuum testing, prepared for movement back to its clean room. Well, you saw it before with its solar array deployed. Here it is in the clean room, preparing for a final solar array deployment. That's the solar array facing you, and it will deploy by flight command here through the computer, through the spacecraft. You'll see the arrays deploying right there. In this, you can also see that the shiny material, that is the thermal protection system. Those are what we call blankets. Those protect it while it's on orbit. This view is how it will look on orbit with the front door opening. And the sun would have been to your right, and this is pretty much how it will look on orbit. And then this is a nice kind of scan view of it fully deployed. This is about the last testing we do before we ship it down to Vandenberg. The next series of videos, we shipped to Vandenberg on April 16th. This is the observatory arriving and being offloaded the truck and being transferred to its handling fixture. It will then be transferred from its handling fixture into the clean room there. If you look quickly, you can see to the left, that is the third stage of the Pegasus rocket. And in the clean room, we do our final preparations and prepare for mating to the rocket. And we do several steps to prepare the separation system and installation onto the rocket. Here you can see the crew in various stages of assembly. That is the separation system being installed there. And this is the orbital Pegasus rocket that will take us into orbit. And that's another view of it. And after we are mated to the rocket, they put on what are called fairings. These are a view of the fairings that are being prepared for installation now, and they will be installed on the rocket at the beginning of next week. We will be launching on June 26th. This next graphic will show you how we get into orbit. This is the Pegasus rocket is actually launched from the bottom of an airplane. It is dropped at 39,000 feet. The first stage is ignited. This is now showing the second stage being propelled into orbit. The second stage, about 131 seconds into orbit, the fairing will separate, and because we're above the atmosphere, the second stage will burn for a few more seconds, and then it will transition to the third stage. This third stage will then put us into our final orbit of 620 by 670 kilometers. When this third stage finishes, it will separate from the observatory and then actually do maneuvers to get away. We will deploy the solar arrays, acquire sun, and go power positive. And then 21 days into the mission, we will open the door and start doing calibrations with light. But to further discuss how we do it, how we get the data down from orbit, and how we operate the observatory, I will hand off to John Marmee.
Thank you, Gary. I'll present a look at operations and data flow for the IRIS mission. But first, though, IRIS is a perfect example of how collaborative efforts between the government, academia, and the private sector can use the expertise of each institution to result in cost savings for the overall mission. I enjoy serving in my role as the assistant project manager, working directly with Alan and Gary on this mission and others at Lockheed Martin to help facilitate this productive relationship. All right, first clip. This clip shows a few of the IRIS team members in the Mission Operations Center at NASA Ames. The Ames Mission Operations Center serves as an example of a small, low-cost flight operations facility for NASA. The Mission Operations Center is staffed 24/7 for the first 7 days of flight. Then when all is nominal, they eventually transition down to one shift per working day. One command load occurs once per weekday, with science and spacecraft health data received daily in a lights-out mode. Next clip, please. IRIS is launched into a 620-kilometer by 670-kilometer sun-synchronous polar orbit at an inclination of approximately 98 degrees. So what's that mean? IRIS flies on the dawn-dusk line and always looks towards the sun. Each orbit takes IRIS on the order of 97 minutes to complete, which allows 14 to 15 passes per day. This orbit was selected to maximize downlink data volume as well as sun exposure time. All right, next clip, please. So after separation, IRIS begins communicating with the tracking and data relay satellite system. Within 15 minutes, the solar arrays should be deployed, and we're over McMurdo Ground Station, Antarctica. Within 60 minutes, we pass over Svalbard Ground Station, Norway. 10 minutes later, we're over the Alaska Satellite Facility. Each orbit or ground track that you see here takes on the order of 97 minutes to complete. Wallop's Ground Station actually comes into view on the 5th orbit. Next clip, please. The primary facilities used to support the IRIS mission are the Instrument Operations Center at Lockheed Martin Solar and Astrophysics Lab in Palo Alto. We have the Mission Operations Center at NASA Ames Research Center. We also have the Near-Earth Network at Goddard Space Flight Center. We have the Svalbard Ground Facility at Svalbard, Norway. We collaborate with the Norwegian Space Center on this mission. We have the Alaska Science Facility in Fairbanks, Alaska. McMurdo Ground Station in Antarctica. We have the Wallops Ground Station, Wallops Island, Virginia. Data eventually makes its way to the Mission Operations Center. We send that off to Stanford to the Science Data Processing Facility, where it is available on the web. All right, next slide. An IRIS day in the life for the team on the ground actually begins with the science team creating a daily plan. They'll take a look at previous images. They'll take pointing requests. They'll take science requests, and they'll also take into account the spacecraft health. They pass it along to the mission operations team, where they begin to assemble the command load. They'll take that spacecraft input. They'll take those sequences, those pointing sequences, those science sequences, and generate the command sequence at that point. They then package that command. They'll have worked with the ground stations beforehand to schedule time. They'll build the scripts to automate that process. They'll verify the command sequence. Approximately 6 p.m. every day, flight controllers then execute commands. They'll establish link with the ground station, upload the command, and then they release the ground station link. After which, telemetry is received. They assess the spacecraft health. They'll send out alerts and notifications. Data is then sent to Stanford, where it's processed, stored. Science data is then posted to the web within 6 hours of receipt, although quick looks of the images of the data will be available within tens of minutes. This solar data is then used in multiple ways to benefit society here on Earth as well as for space exploration. Next slide, please. So the IRIS mission starts with launch. Separation occurs 13 minutes after launch. The spacecraft detumbles, opens the solar arrays, begins communicating. So for the next 30 days, we check out the instrument. We check out the spacecraft. On day 21, we open the telescope door. The science campaign officially starts on day 60 as we begin our exploration of the sun. For the next 2 years, we're in nominal operations. So given there's no fuel on board, if after 2 years the observatory is healthy and productive, NASA then has the option to extend science operations. Theoretically, IRIS could be productive for a few decades if the observatory is healthy. And that is a look at the IRIS operations for this exciting mission. So back to you, Steve.
Okay, thank you, John, and to all our panelists. Now we can go to questions. If you're on the phone bridge, reporters, and you'd like to ask a question, please hit *1. If you're watching online and would like to ask our panelists a question on Twitter, use the hashtag AskNASA. We also have graphics online. Everything you've seen here is available online. You just need to go to a website. It's go.nasa.gov/iris graphics. There's the URL right there. Okay, we'll start our questions from social media. I think we have some from Twitter.
Thank you, Steve. The first question that we have for the panel is, what do you hope to discover or find during the IRIS mission?
What we want to discover is what the basic physical processes are that transfer energy and material from the surface of the sun out to the outer atmosphere, to the corona. And remember, the corona extends throughout the heliosphere. We live in the sun's outer atmosphere.
Okay, another question from Twitter, please.
Thank you. How many pixels will the images that IRIS takes have?
We have 3 CCD detectors that are roughly 2,000 by 2,000, but we won't use all of them all the time.
Okay, and we have one more question from Twitter before we go to the phone lines.
Okay, thank you. How far away from the sun will IRIS be while it's taking its measurements?
IRIS flies around the Earth, so it only gets about 600 kilometers closer to the sun than here we are on Earth, and that's about 92 million miles away. So it's really not very much closer to the sun.
It just stares a long time.
Okay, and now we have a question from the phone bridge, Denise Chow at space.com. Go ahead, Denise.
Hi, thanks for taking my question. I think it's for Alan. What happens in the interface region during solar storms, and are you expecting IRIS to see changes during solar maximum?
Absolutely. The second view of the sun, the one that showed the region around a sunspot, showed the kind of activity that happens in a rather quiescent active region. So regardless of exactly where we are in the solar cycle, and right now we're pretty much at solar maximum, we're going to see a lot of activity. And we have pre-planned a large number of observing sequences that are targeted to seeing things like solar flares.
Our next question is also from the phone line. It's Alex Whitsey from Nature. Go ahead, Alex.
Thank you. My question is also for Dr. Teitel. I wanted to ask about this Swede balloon experiment that will be flown over Sweden also this summer called Sunrise. How will that complement or not complement what you're doing with IRIS?
Well, unfortunately, the Sunrise flight is supposed to be in the next few days. Now, that's nice for Sunrise. I wish that it had flown at the same time as IRIS, but I guess that's something that just didn't happen. But Sunrise is a very important, very highly capable experiment, and it will tell us a lot about the smallest magnetic field structures on the sun. And the more that we know about the driving magnetic fields, the more easily we'll be able to interpret the results that we get from IRIS.
We have another question on the phone lines. Rebecca Boyle, freelancer. Please go ahead, Rebecca.
Hi, everybody. One of my questions was just asked, but I have a quick follow-up about it. I guess, how could balloon missions like Sunrise or sounding rockets like the High C mission complement what you're doing with IRIS? Could you sort of have a fast reaction possibly to something that you've seen with IRIS and send up a quick balloon or sounding rocket to take a further look?
I guess that's really a question for Jeff Newmark. That I would hope that the combination of IRIS and the Solar Dynamics Observatory and observations on stereo